So we're going to finish out this QSPR spreadsheet tool, and I think it'll be enjoyable. We're going to turn this regression analysis, which we have here, and the performance plots into a spreadsheet tool. Right now, it's more of an analysis. We solve for the relationship matrix that turns the molecular formula, carbon, hydrogen, nitrogen, and oxygen, into various properties. We did the molar mass, we did the molar volume, and then the enthalpy of combustion. And it was pretty good. Here's the molar volume, QSPR. Our model is on the y-axis. The literature values are on the x-axis that are determined from the molar mass and the density. Over here is the lower heating value. It's even better. Wider range of values. And so these are our relationship matrices that we solved for. I'll go ahead and put this one in yellow too. Actually, no, we didn't paste in the relation matrix for the molecular weight. Pardon? Yeah, it actually turned out to be, essentially the model that was used to generate that column. Not yet. So, but one thing that we're missing in this spreadsheet up here at the top that I would like to see in your projects is, what this spreadsheet is. So typically this upper left-hand corner of the sheet, that's where you put your information about what it is this calculates, who wrote it, and when. And so go ahead and up here, type in your quantitative So I'll put in quantitative structure property relationship worksheet and hit enter. Of course, I'm going to fix this. It's centered, so we'll make it left justified. Just skip all of these. And we'll say November.
You write down over here.
No, y'all put your names in there. I state my name. I state my name. Yes. Yeah. Well, you did the regressions. Okay, I put the date, and then, if you share this with somebody, and then they use it to do, all kinds of great things. You can pick your level of copyright. There's different levels of copyright. I forget, I should have prepped for that. But yeah, you can go on to look at the Creative Commons copyright standards and so on. But basically, my copyright standard for these spreadsheets is you're free to use and modify with attribution. So that's all it is. So you can type that into copyright. And so that's, you can claim more restrictive rights if you want, but those are the ones that I like to use. That just tells somebody who has this spreadsheet who made it, when they made it, what it does, and can they use it or not. And if they can use it, what are the requirements? What are the restrictions? Do they have to send me $20? You can put that in there. This is not shareware. This is not freeware. You got to pay for it. There's a bug in here that's going to, kill your results unless you pay me or something. I'll send you the code. No, mine is just free to use with attribution. And so if you were to use this, then you would put in your bibliography or so on. Whenever you cite the spreadsheet in your experimental or what have you, then you put a reference mark, and then you could say, according to the ACS style, whatever their particulars are, spreadsheet provided by Darren Williams, Sam Houston State University, blah, blah, blah. Okay. And that's really a handy thing. That way, when you do it, then you can share your stuff to others, and then if they use it, they can attribute it, and so on. You pass it on to the students behind you, and they use your tool and their thesis work, and you'll be in their thesis bibliography section. And you'll have a legacy that goes on, and 20 years later, you'll read somebody's thesis and they're like, my gosh, they're still using that spreadsheet tool that I made. That's amazing. So it's always exciting to see your name in print. Okay. So those seem like minor details, but they're not that minor. You know, it's very good to have these kinds of things put in there. Okay, so this was the training set, as you notice from the page. And so what I would like to do is create a new sheet down here. And we'll double click the name and we'll call this QSPR. Okay. I think I'm going to move this tablet so I can scoot my laptop closer to me. Okay. There we go. Okay, so what we're going to do now is we're going to create some columns for our carbon, nitrogen, oxygen, and fluorine. Let's come down here to like 5th row. Let's make it bigger. So C, H, N, O. And if we have a name, we could put a name cell in there. Okay. And then what were the different models that we had? We had molar mass, right? Let's see, let me try to figure out how we're going to do this. It's going to be this row times the first column of our QSPR added together to give us a single number. Yeah, okay, so it's gonna give us a row of values. So what we're going to do here is we're going to put these over here to the right. Okay, so molar mass. And you can come up here and see this little thing called word wrap. Word wrap is really helpful. Okay, so we're going to word wrap this. And let's go ahead and put it on the same row with our headings, actually. So we had molar mass, we had molar volume, hit the wrap text button again. LHV, so lower heating value. If you want, I mean, it's probably proper to put our units. So this is kilojoules per mole. We can go and do that for the others too. Yeah. All right, that's fantastic. So those were our 3 QSPRs that we had. Okay. Let's go a couple of lines down below the name value and type in QSPR relationship matrix. Then type a C, H, N, O. Take these 3 headings that we just made and control drag them down here too. So we're going to copy them down there. Everybody see that? Yeah, we're building something interesting here. And so this block of data right here are going to be our matrices. You know, let's go ahead and add. We got to actually add a row here because we need that intercept. Intercept. And let's scoot all these over to the right and we'll put an intercept here. And we'll just put a 1 there. So this will help us with the matrix mathematics. So we got, yeah, okay. So now we've got everything pretty well set up the way we need it. So let's go get our relationship matrices for all three of these. So go over to the training set. We'll actually get the periodic table relationship matrix for the masses. So we're going to select these 4 values and we're going to copy them. So Control C. And then go over to the QSPR and put that under molar mass. Control V. And then to do the same thing for the molar volume. So we come over and get that relationship matrix. We could get it out of our ANOVAs too, our regression analyses. I don't like the highlighting right now. Just let me get rid of that. Okay, and then let's do the last one, the lower heating value. Copy. And I'm just going to paste the values here. Okay. So this is now an interesting thing. These are all of our QSPRs in a matrix. What's wrong, Felicia?
Just taking a little longer.
Okay. Okay. So I'll pause here until everybody's to this point. Okay. Yeah. So what we're doing is we have that training set, we've created these relationship matrices, and now we're going to use them. So we're going to create some neat values that where we can type in a compound and have it use our QSPRs. Okay, so let's come up here and let's do acetylene. And so that's 2 carbons, 2 hydrogens, 0 nitrogen, 0 oxygen. So there's our structure, and then we have the relationships, and we're going to model the properties.
Row times column.
Yeah, row times column. Okay, and so we have now select all 3 of these cells here. Okay. Does everybody have that? You select all 3 of these cells, then you type in mmult, open parenthesis, and then we select all 5 of these cells, because that's our structure, and we're going to run this or matrix multiply it against the property matrix, the relationship matrix. And so then we come down here, we get all, what is that, 15 of those cells. So we see we have that intercept through carbon, through nitrogen, oxygen row times the column, and the first column is molar mass. And it's going to add all those values and give us the molar mass. Then it's going to move to the second column, add all those values and give us the molar volume. And then it's going to move to the third column, add all those values and give us the LHV, all in one step. So we close the parenthesis and hit Control Shift Enter, and there's our 3 values for acetylene.
Molar volume's a little off.
Yeah, it could be. Yeah. It's kind of weird too. It's a gas, so I don't know exactly.
The real one is 22 apparently, or the experimental one is 22.3.
Molar volume, really interesting. Yeah. And so that brings up a good point. You know, we didn't have acetylene or molecules that were necessarily that unsaturated in our training set. And so if you don't have that type of molecule in your training set, you're going to miss the particulars about that type of molecule. Okay. Now let's do hydrogen, just H2. Okay, so let's put a 0 in for the carbons. Okay. So you can just play around with this. Of course, the name didn't update, but but you could put in any molar mass or any molecular formula there, and you can get all of these values for it. So what we did in PChem 1, which was fun, I thought, is we calculated these QSPRs, and then we had a lot of what I call derivative values. So these are values calculated by our quantitative structure property relationship, but then there were other values that were derivative from those calculations. I'm just going to center all of these so that it lines up a little better. And so what do we have? If we've got the molar mass and the molar volume, we could take the ratio of those and get the density. Okay, so let's make a density here. D density equals molar mass divided by molar volume. And so there's our density. Yeah. You know, we don't typically buy, like if you go to the gas station and you buy fuel for your car, let's do hexane. Let's make a typical fuel here, hexane. C6, what is it, 12 and 14, so 14. Okay, so there we have our molar mass, our molar volume, our heating value, kilojoules per mole, density. But we don't buy our gasoline, like hexane, we don't buy it by the mole. Okay. Oh, so if you're in an industry, you buy it by mass. You buy, so many pounds. And so we could calculate the energy density in terms of kilograms per gram. So we have kilograms or kilojoules per mole, and we have grams per mole. So let's find the energy density in terms of mass or specific energy of combustion.
kg per gram or kilogram? Per kilogram?
We could either way, specific energy of combustion. That's going to blow up our word wrap. And so I'm going to call this kilojoules per, let's say kilogram, yeah. But then I got to make sure I get the units right. So this is going to be equal to the kilojoules per mole divided by the grams per mole, okay. And what do I need to do? Multiply, what's that? Divide by 1,000? Okay. No, I need to multiply by 1,000. Grams is in the denominator.
Oh, yeah.
And so I need 1,000 grams per kilogram. So times 1,000. So that's how many kilojoules per kilogram. But if I'm, not an industry, if I'm at the actual gas station, I don't buy it by the mass. They don't put my car on a scale. Right? How do I buy fuel? Buy it by volume. Let's pretend we're in Europe. Let's do, liters. Okay, so kilojoules per liter. So this would be the energy density. So that's equal to the heating value divided by the molar volume, again, times 1,000. So 30,000 kilojoules per liter of hexane. So this is pretty neat because now I have a number that's useful. How many kilojoules do I have in a liter of hexane? I've got 30,000 kilojoules, 31,000 kilojoules. And, yes, I could use per mole and all these other numbers, but this is a really practical number. If we wanted to convert that to gallons, how many gallons do we have in a liter? Anybody have that? Does anybody?
3.78 liters per gallon.
3.78?
3.785 liters per
Okay.
gallon.
So
So if you want to go backwards, or if you want to
So we want to multiply that by 3.78.
to get to liters,
Yeah, so we take this,
to get from liters.
yeah, equals this number here. So liters is in the denominator.
So we should be
Multiplying by, 3.78.
to 75.
Okay, that's good. All right, so then we have 117,000 kilojoules per gallon. Okay. Now, most cars, I mean, this is just my DW's rule of thumb. Okay, I haven't read this anywhere, so that I don't have a good literature source for this. But in my experience of buying cars, or mostly pickup trucks, okay, but even Suburbans, the target for a full tank of gas is about 400 miles, right? And if you got a little bitty car that gets really good gas mileage, you might have a 15-gallon tank, right? You have a Suburban like I had, it had a 42-gallon tank. Still 400 miles though. Right? So actually it was a little better than that. But the point was the target for a full tank, let's say an average car was a 20-gallon tank and that was 400 miles. Okay, so right there is kind of a conversion factor. 20 gallons, 400 miles. Okay, that's 20 miles per gallon. So average, mileage, 20 miles per gallon. So how many kilojoules does it take to go a mile here? We could figure this out. We could do kilojoules, and how much this sort of hexane's our general fuel. How far could we go on a gallon if it's 20 miles per gallon? How many kilojoules per gallon? So you could use this. This is an example of a derivative unit. Okay, so a gallon is 20 miles, so equals. Let's see. Let's change this. So kilojoules per mile. Sorry.
So energy, just energy per distance.
Yeah. So and so we have let's see, per gallon, and so it was like, let's say 20 miles per gallon. Oh no, this is kilojoules times miles, right?
Yeah.
Yeah. Yeah, because gallons is in the denominator. No, that's right. That's right. Yeah, that's right. So we divide by 20 essentially. So it's equal to that per gallon. Each gallon is 20 miles. Okay. And so we multiply by 20. Let's see, per gallon. And then gallons on top, 20 miles is on bottom, so we divide by 20. Yeah.
There we go.
Yeah. So that's how many kilojoules it takes to go a mile on hexane. Again, this is DW's rule of thumb. It's not published. I don't know, but it would be an estimate. But my point is that you can get as creative as you want. These would be called derivative values. We have a quantitative structure property relationship that tells us how many kilojoules we have in a mile of driving a standard vehicle. And we got that from the molecular formula. So it just shows you the power of just thinking through these problems and coming up with creative relationships. Okay. So let's change this to octane. See what we get. Does it get better? So then we have 8. Okay. 18.
I didn't see it get better. Oh, you got a little better.
What's that?
I was just see if better machine.
Yeah, so it seems like
A little bit higher.
yeah. So we have a little bit more kilojoules per gallon. Okay. If we're still only getting that same gas mileage, then it's not as good. But our energy density is improved. Let's go to benzene. So if we could just take our old solvent, benzene and toluene and those kinds of things. So that's C6H6.
Even better.
Yeah, even better. Again, what this is not doing, it seems like it's bad with the kilojoules per mile. That would be if we were still only getting 20 miles per gallon, we would be using so much more heat to go that same 20 miles. And so that's why it looks like the kilojoules per mile is getting worse, because we've sort of capped that at 20 miles per gallon. But I think we'd go to that number above it. So the kilojoules per gallon has gone up. And so we'd be actually getting more energy per gallon out of the pump. And so I think that's good. And in fact, it was substantially better. If we look at that number, 126, 126,000 kilojoules per gallon, and we hit undo twice because that will change our values back to octane. So I'm going to do undo twice. 120, okay, versus 126, really 127. So we got another 7,000 kilojoules per gallon by going to a more unsaturated molecule. Does that make sense from our model? Let's look at our model. So we can actually go in and look to see what the coefficient for carbon is. This is kilojoules per mole. So for every carbon atom I add to my formula, I get another 400 kilojoules. Every hydrogen I add, I only get 103. Yeah, and if I add nitrogen, I get 122 using our training set. But oxygen's negative. Every oxygen I add to the molecule, I actually lose energy.
It's already oxidized a little bit.
What? Yeah, it's already partially oxidized. This makes sense? So even though it looked like it was just statistics, we can actually see some of the chemistry that's happening here. So hexane is better, than let's see. Octane was better than hexane. Hexane is probably better than pentane. So we're getting more and more carbons.
Still protein.
But look at benzene. We got rid of some hydrogens, added some more oxygens, and we get even more energy output.
Sucrose.
Yeah. It's none of those carbohydrates are in our model, so who knows what they would give. But we'll do it in a second. Yeah. So let me look at the difference between. I don't know.
Oh, I would not put sugar in your car then. This is bad.
Let's do propane. Okay, C3. What is that? H8.
Yes.
Okay.
Yeah.
And I'm going to put that number over here, kilojoules per gallon. 103.869. Okay. Let me rearrange these numbers. Okay. So, sorry for fiddling around with the cells. Okay.
Like that.
Yeah. And so I've got propane there, and let's do propanol.
So keep the number of hydrogens set up.
Yeah. Just add an oxygen. Big difference.
Propanolic acid.
Yeah. But I'm just thinking, what does this say about this big push for putting ethanol in our gasoline? Yeah, so if we're removing, we had hexane in there. Let's do C6, H14, no oxygens. Okay, so hexane here. 116777, and then ethanol. Let's do ethanol. C2, H6O. $76,970. Again, it's partially oxidized, so that's working against us. We're putting already oxidized carbon in our fuel tank, and we're getting less energy out of it. And there's no controversy here. You put ethanol in your fuel, you're going to get less energy per gallon. Okay, and we even saw this statistically from our lower heating values, in our QSPR. So you could use this simple QSPR to find the optimal fuel. You could see, and so you could play around with it. Something. I mean, if you could make something that was totally unsaturated, like polyaromatic hydrocarbons, lots of fused rings, then you'd have a really good fuel. You'd have a lot of energy per mole and per gram and per volume and so on. But the problem is some of those molecules start to solidify, and so their physical properties start to harm you. That they don't flow. You can't pour them out of a pump. You can't put coal in your gas tank, right? But if you had, things, again, unsaturated fuels like benzenes and things with the high DBE, so that's a petroleum term, the DBE, for double bond equivalent. And so they'll take the oil mixes and they'll say, well, this fuel has a higher double bond equivalent. It has a higher energy value, a higher heating value. And so we see that from our QSPR. Okay, so we've pretty much finished up with this QSPR. And this would be a moderately useful tool. We can take our little titles from this sheet. Let's go ahead and put them on this other sheet. And now I need to write out to the user what to do. So I'm going to put a yellow highlight on this row here. And I'm going to put a yellow highlight right here. So I'm putting in instructions. Only edit the highlighted cells, right? So you're telling yourself later or telling someone that comes behind you what numbers are changeable or should be changed and what numbers should not be changed. Then enter the name and molecular formula to use the calculator. And this is a really simple spreadsheet, so that's really all the instructions that I need. And now if I'm making this as a tool for someone to use, I've just got this random table here, and that's a problem. Okay, this is something I will count off for. So when you make your little tools and you've got some stuff in here that doesn't change with the calculation, it just seems like a random table there, you need to reduce the amount of distracting information. And so this random table is useful to kind of show that the thing's still working. And so you might go ahead and just scoot this down or move it someplace else and say, maybe put example calculations. Example results. How about that? That way I can say, all right, if I type in those compounds, I should get those numbers. And now that's no longer a random table. It's a useful thing. It tells me I can practice with this and I can do some calculations and see if they match what the example calculations were. Okay. Yes?
Nowhere in this did we define the 20 miles per gallon type thing.
Oh, excellent. Yeah. Okay, so then we might put, let's see, under kilojoules per gallon and gallons per mile. So I'm going to put right here, I'm going to right-click this. And look here, here's an insert comment. Okay, so I'm going to hit insert comment and it pops up and it says using the rule of thumb of 20 mpg as per Dr. Williams. Okay. And so now when I come down here, I'm like, kilojoules per mile. How do they do that? I hover over this cell and I see this little tooltip or comment that pops up. And that's nice. It's not distracting. I don't have to have lots of explanatory text in there. But then if I'm using the spreadsheet, I can have these little comments that pop up. And that's a very nice thing to do. Okay. So that's a great observation. So this would be one of the examples. In fact, this is one of your examples. You get to now clean this up, make it yours, You know, if you don't like my layout, great, make it your own. And so this would be one of the things in your portfolio is this little QSPR tool. If there's another property that you use in your area or that you're interested in, do a little QSPR and add a property to it. You know, like if you've, you know, let's say you've got this pKa QSPR, it's a small training set, but if you had a bigger one and it was DPH values, if you could type in the DPH values and get the pKa with the spreadsheet tool, then you know you could look at other bases really quickly and just sort of use that QSPR to see which one has a pKa that you're interested in.
Thinking about it, I think I actually kind of use something like this in my research already.
Yeah.
Calculating theoretical values for hydricity and pKas.
Yeah.
So.
Yeah. So what I was saying, you know, you could perhaps make, and maybe you don't have a full-blown QSPR, but you've got some formula or something. And even if it comes out of the literature, all the better. You don't have to do your own regression. If you find a useful calculation from the literature that you're going to use, go ahead and make a spreadsheet tool for it, and then include that in your portfolio. I think it'll be pretty easy. You've already done two, the sphere, the HSPIP sphere, and the QSPR. So you've got two major spreadsheet tools there, and for you to come up with three more shouldn't be a problem, you know, related to either your interest or your research or just general science. And like that student that graduated, he made all of those volume calculators for cylinders, like drums to gallons to mass for, you know, hydrocarbons and so on. Yeah.
So we're gonna make it so our spreadsheets can stand alone. We're not typing up a report.
Yes, that's a great question. Yeah, I want your spreadsheet to stand alone. So you'll turn in the spreadsheet. Now, your models, just for simplicity's sake, this may not be in the long run very practical, but I want them all in one workbook. Okay, so each sheet, yeah, so a sheet would be for the QSPR, and then a sheet for the solubility sphere, and then a sheet for hydricity or whatever. If it's Will's, or for yours, it might be something related to the proteins, you know. And so you'll have in that workbook all of your sheets, but in reality, you'll probably have a different workbook for all of these different things. And so, but as far as grading, I'd like to have a single workbook per student, and I could look at all of your sheets.
So
And I
no
could,
additional report to explain anything.
right, yeah, everything should be sort of standalone. If you gave somebody a thumb drive with all your workbooks on it, they should be able to open that workbook and see in the upper right, upper left, who made it, what it does, have some instructions. Now, some of these instructions are going to be pretty complex, right? So you may have to have a separate sheet with just instructions. Like think about the solubility sphere. So you may have to have a procedure page for the solubility sphere and then a calculations page. Okay, so go ahead and do that. That way you can have, you know, step one, you know, expose your solvents and your solutes and everything like that, score them, you know, and so you can have a procedure page that allows you to use the calculations page. And with that, let's wrap up, put the laptops up because we're going to bump up against over the edge.
Quick question.
Yes.
You're saying a procedure page, you're like using a worksheet?
Yes, as a procedure page, yeah. So that procedure page will just be instructions for doing an HSP sphere, and it'll be, you know, step 1, 2, 3, 4, and you'll just type it into those rows. Okay. It's not exactly ideal, but it's convenient. You know, you get a workbook and it has the procedure right there in the workbook, and it's really convenient for someone to use.